Hello everyone, my name is Gharisa Almheiri and my colleague Azizeh Mohammad from Abu Dhabi University. Today we will present our paper which is Sustainable Approach for the Production of Biodiesel from Waste Cooking Oil using Static Mixer Technology. Our agenda for today, we will start with a general understanding of the concept of biodiesel and how will it contribute in UAE sustainability vision. Then we will go through the process description and process calculation, which is mass and energy balance. After that, we will go through the reactor design, economy analysis, and finally the conclusion. Biodiesel is chemically known as fatty acid alkyl ester in organic liquid fuel that is used as a substitute for petroleum diesel and derived from different vegetable oils and animal fats. Generally, waste oil is used and preferred over fresh oil as it manages a huge amount of oil from the disposal to water and land sources. This fuel is biodegradable, non-toxic, free of sulfur and aromatics, and safer to handle and transport. In addition, it can be used in almost all compression ignition engines without the need of any modification, and has superior lubricating properties, making it as an excellent alternative fuel. The biodiesel synthesis can be either pyrolysis, direct blending, microemulsion, or transesterification, which is the most common among these processes. Compared to transesterification, pyrolysis process cost is high, as the separation of biodiesel from the other product is quite difficult. Microemulsion have low stability and requires more surfactants that is quite expensive to maintain in state, and direct blending method result in an insufficient combustion and increase in the production of carbon monoxide and particulated matter. In this work, the production of biodiesel is going to be conducted using the conventional method, that is transesterification, since it improves some qualities of the waste cooking oil such as the viscosity, cetane number, and flash point, resulting in a good biodiesel quality. In UAE, the produced waste cooking oil is either dumped in drainage or disposed improperly in water due to its insignificance, which cause clogs of the pipes and disrupt the marine ecosystem. Al-Bayan has published an article in 2013 saying that almost 292 tons of oil is used yearly in UAE. And based on an article published in 2018 by Gulf News, Abu Dhabi produces 20,000 liters of used cooking oil every day, and about 14,000 liters of waste cooking oil is produced from Dubai restaurants and hotels. In total, almost 300 liters of waste cooking oil is produced every day. So, utilizing these huge quantities of oil in green processes for the production of biodiesel result in the economic growth of the country and support UAE Vision of 2021, aiming in preserving water resources, increasing the contribution of clean energy and implementing green growth plans. To start the biodiesel production process, the waste cooking oil stream entered to the filter to remove solid particles resulting from frying process. Then the filtered oil will preheated in the heat exchanger using the esterification reactor product and fed into the esterification reactor to convert the free fatty acid to methyl ester. During this reaction, fresh methanol will mix with recycled methanol and sulfuric acid. The product of the esterification reaction are cooled in a heat exchanger which is used to preheat the oil feed simultaneously, and then sent to a membrane separator to separate water, methanol, and sulfuric acid totally from methyl ester, triolene, which is the unreacted oil, and remaining free fatty acids. The stream that contains methanol, water, and sulfuric acid is charged into a distillation column to recycle most of the unreacted methanol into the esterification reactor again. And the bottom product mostly contains sulfuric acid and water was treated as a waste. The pre-treated oil from esterification process, which is stream 108, that is present in the membrane separator is then sent to the transesterification reactor. Before entering to the 4 parallel transesterification reactor, a fresh methanol is mixed with recycled methanol, which is mixed with potassium hydroxide. Since the catalyst is in the solid state, it is dissolved with methanol in a separated mixing unit, and then the product of the mixing is heated up to 60 degrees Celsius before entering to the reactor. The product of the transesterification reactor are fed to a vacuum distillation column, where most of the methanol is recovered and recycled back to transesterification reactor, where it is mixed with the fresh methanol. The bottom product of mostly containing biodiesel and glycerol is charged to a washing column, where water is used for biodiesel washing from the leftover methanol, soap, glycerol, and catalyst. The top stream leaving the washing column mostly containing methyl ester and unconverted oil is fed to a vacuum distillation to separate the remaining methanol and water from biodiesel and unreacted oil. To achieve a biodiesel with a high purity that matches ASTM specification, stream 501A is fed into a distillation column. The overall head contains water and methanol, and the bottom stream leaving the column mainly contains FAME. The unreacted oil is obtained in the column bottom stream 502B. The bottom stream leaves the washing column containing glycerol is fed into a neutralization reactor to remove the catalyst. Phosphoric acid is added in equivalence mole of potassium hydroxide that is existing in the stream, and the resulting salt and potassium are removed and treated as a waste using horizontal gravity separator. The resulting glycerol from the neutralization reactor is further purified in distillation column. The top of the column contains water and methanol, which is treated as waste. The column bottom stream contains glycerol with a 91% purity. There are 2 overall reactions for the production of biodiesel. The first one is the conversion of oleic acid to biodiesel through esterification reaction in the presence of sulfuric acid as a catalyst. And the second reaction is the transesterification reaction, where triolene reacts with methanol to produce biodiesel and glycerol. Mass balance calculation were done based on the general equation, which is input plus generation equals to output plus accumulation and consumption. And since the overall process was assumed to be steady state, the equation is simplified into input equals to output. And for reactive system with X conversion, the following equation is used. Also, for this process, we assume that 150,000 tons per year of waste palm oil is used, and the palm oil consists of 64% of triolene and 6% of oleic acid formed by constant frying, and 330 operating dates is considered. Thus, 22,000 mole per hour of oil will be used as a base for the process calculation. The following table shows the mass balance result for the whole process. The general energy balance equation was simplified to delta H is equal to H out minus Hn, as there is no change in kinetic energy, potential energy, and shaft work. And for reactive system, the extent of reaction was added. And for pump, the following equation was used, which is delta H is equal to V delta P, where temperature and pressure data was obtained from literature. And the following table shows the energy balance result. This negative number determines the loss of energy, and 0 shows that there is no change in energy. Static mixers are used as a reactor for this process rather than conventional CSTR due to their better mixing ability, less energy consumption where there is no mechanical stirring, and it requires less maintenance because there is no moving parts, and more compacted geometry, which means less space consuming. Also, the static mixer in this work was assumed to be a standard Sizzler SMX element, containing one crossbar, 3 parallel bars, and 90-degree angle between opposite crossbars. As for the design, in this work 7 main process equipment were considered for modeling, and the rest were either scaled up or down. In this presentation, we will focus on the design of the main reactor, which is R200, that carries the main reaction for biodiesel synthesis. The rest was designed based on heuristics and conventional equation, and the final result is present in the paper. For the reactor, and to achieve the laminar flow, the input stream was splitted into 4 identical parallel plug flow reactors with a configuration similar to 1-2 splitter ring shell and tube heat exchanger. Each reactor contained 400 tubes and 200 in each pass to further reduce velocity and Reynolds number to achieve laminar region. Also, the mixing in each tube occurred by the mixing element rather than the conventional CSTR, as it enhanced the mass and heat transfer between the reactant, thus increasing the conversion. From different literature review, conditions of 6:1 ratio of methanol to oil and 1% of KOH was considered, which provide a conversion up to 90%, but the design aimed at reaching a conversion of 90% of waste cooking oil into biodiesel. From lecture, the kinetics for the reaction was found to be 0.019. Using PFR sizing, the volume was found to be 45.7 meter cube, with dimensions of 0.62 meter and a length of 33 meter. The total pressure drop includes the pressure drop of the empty pipe and including the pressure of the empty pipe and the mixing element. For the pipe, it was found to be as 181.7 Pascal, and for mixing element, it was calculated as 2.18 kilopascal. The Z factor of the pressure drop was found from literature. To calculate the total cost of manufacturing, fixed capital investment, cost of operating labor, utilities, water treatment, and raw material is required. So we calculated the total cost of equipment using the total module cost equation, and we find it to be $4.8 million. Then we calculated the total grassroots cost, which is fixed capital investment, and we find it as $8.1 million. After that, we calculated the revenue from the two products of the process, which is biodiesel as a main product and glycerol as a byproduct, by multiplying the product cost per kilogram by the annual mass flow rate. And we find that the total revenue of biodiesel is $142 million per year and $10 million per year for glycerol. For the profitability analysis, a 10-year plan was considered with 2 years of consideration and a double decline method for calculating the depreciation. The working capital was assumed to be 20% of the fixed capital investment, where 60% of the fixed capital investment was used in the first year and 40% was used in the second year of construction. Land cost is assumed to be 6% of the fixed capital investment. The tax was considered as 5% as per UAE's law. The following table represents the undiscounted profitability with column of planned year, investment, depreciation using double decline method, sum of depreciation, fixed capital minus depreciation, revenue, cost of manufacturing, tax, cash flow, and cumulative cash flow. The investment in year 0 is equal to the cost of land, and in the first year it's equal to 60% of the fixed capital investment. At year 2 it's equal to 40% of fixed capital investment plus the working capital. The plant start to operate in third year, so no investment were added to the company, and in last year of the project the company get back its cost of land, working capital, and the salvage value. The cost of manufacturing is added after year 3, that is when the manufacturing start. And we obtain the following result. The payback period is 1.5 years and cumulative cash flow position is 38 million. Cumulative cash ratio is 4.98 and the rate of return of investment is 51%. Further, this graph represents number of years versus cumulative cash flow. This table represents the discounted analysis. The net profit value is the last value in the cumulative discounted cash flow, which is equal to 56 million. The discounted cash flow rate of return that will make the net positive value equal to 0. Using the Excel, we find it to be 38.74%. So, the discounted fixed capital investment was found to be $1.3 million and the payback period is 5.3 years and the discounted rate of net profit value is 0.38. The aim of this work was to design a chemical plant that produced biodiesel from 150,000 tons of waste cooking oil collected from various hotel, domestic areas, and fast food restaurants. Various pathways for biodiesel synthesis was investigated, and the process with highest product quality, higher profitability, and consumed least amount of energy was selected. And a biodiesel with high purity that meets the American Society of Testing and Material Standard was to be achieved. The intended outcomes were achieved through literature review and energy calculation were done on all equipment in the plant. And to achieve 90% conversion from oil to biodiesel were found. Further, a detailed equipment design was done on the main equipment such as distillation column, reactor, and pump, in which the cost of each equipment was found to calculate the profitability analysis for discounted and undiscounted cash flow to determine the feasibility of this chemical plant. Thank you.